Assalamualaikum warahmatullahi wabarakatuh. Good afternoon. Today we will continue our class in electronic instrumentation design, and we jump to the next chapter. Chapter 3 in the textbook is signal analyzer. And to discuss this chapter, we will have 2 weeks, and this is the first week for signal analyzer. Okay. In previous chapter, we already discussed about the different type of instrument that are used to generate various waveform. We discussed about the function generator, waveform generators, and so on. And to evaluate the quality of the waveform generated, distortion and stability of the output, such as a signal generator, the instruments like signal analyzer is required. Many types of signal analyzer. In the textbook, we know that we have harmonic distortion analyzer, wave analyzer, and spectrum analyzers. So the first one, we will talk about the wave analyzers. So this instrument is measures the relative amplitude of the single frequency component in complex or distorted waveforms. So this can also be regarded as a frequency component that can be selected and its amplitude can be determined. The circuit is tuned to the particular frequency and all the other components are rejected. So wave analyzers is used to analyze the waveform or generated by like a function generator. So we have a figure 3.2. This is the block schematic of an attenuator, and also this is the frequency response of the high pass filters. The first, if we have the signal that to be analyzed in wave analyzer, we have to apply it to the input attenuator, and then signal go to the input amplifier or driver amplifier. And then after, so this is the input amplifier or the driver amplifier. After going to the driver amplifier, the signal coming to the high Q active filter, and this filter consists of the cascaded arrangement of RC resonance sections and auto filter amplifier. So this is the high Q filter. And then after the signal that we want to analyze is already filtering in this high Q filter, then the signal is coming to the output amplifier or the final amplifier stage and then given to the meter for the analyzer. Okay, so the attenuation characteristic of the instruments, I mean that before the driver amplifier, we go to the attenuator, and this is the attenuator characteristic. The initial attenuations at 1/2 is about 600 dB per octave, or we can see here the attenuations at 1/2 and twice the selected frequency is about 75 dB. So this is the attenuator, and then this is the frequency of interest, and this is the before bottom lower of the frequency of interest here, and then this is the upper level of frequency of interest. So in the frequency of interest, there is no attenuation, or attenuation is 0. But in below of the frequency of interest, or the upper of the frequency and interest, we put an attenuator here, and then we go to the input amplifier, and then going to the filter output amplifier, and then we can see in the meter for the analyzer. And the second, okay, so this is the frequency, and then this is the frequency sound of high pass filter, and then the instrument number 2 is the AF wave analyzer. So we can see from the block diagram that from the AF wave analyzer, it we can tune the R here and C here to get the frequency of interest of our frequency, and then the measurements is around megahertz. So the AF wave analyzer, we can measure or analyze the waveform until in megahertz range. And then we can see from here the input signal to be analyzed in uh, heterodyne to a higher intermediate frequency range. So the signal input coming to the input attenuator, and then going to the output amplifier, and then we can make a variation of R and C to tune the frequency, and then the signal coming to the filter amplifier, and then after coming to the second filter amplifier is coming to the meter range attenuator, and then going to the output amplifier, and then after that we can see in the meter amplifier and detector to see the analyze of the waveform. Okay, so the output of this wave analyzer from the meter analyzer we can check in the megahertz range. Then the next analyzer is high frequency wave analyzers, and comparing to the AF wave analyzer, in high frequency wave analyzer we can analyze the waveform in little bit higher frequency, and in the receiver the input amplitude modulated EM, and also the radio frequency signal carrier, we have to combine it with the local generated RF signal in order to produce a signal at a new frequency or IF. So we know that we have the mixer here. This is the mixer, and this is the receiver. So this is the receiver. So I put this is the RX, and coming from this attenuator is the RF signal, and then we have the local oscillator here, the local oscillator, and then we have to mix the RF and then the frequency of local oscillator, and here is 30 megahertz to get the IF frequency here. And then we have two methods for this high frequency wave analyzer. The first one is multiplication type in a wave devices, and the second is additional type in a non-wave devices. And this is the block diagram of a wave analyzer. As I mentioned before, in the receiver, we receive the signal in RF signal, and then coming to attenuator, and then coming to untuned amplifier for the amplify the coming signal, and then coming to the mixer to mix the RF signal coming from the input with the local oscillator here to get the IF range here. And then coming to the second mixer, this is the crystal oscillator, and then maybe a little bit a lower frequency mixer, so we get the IF range a little bit lower than before the second mixer, and then going to the active filter for the bandwidth adjustment, and then we got the signal here, and then we can analyze signal in the meter. Okay, and then this is the simplified block diagram. The coming signal is RF amplifier, and then we have the mixer here to mix the local oscillator frequency here with the RF amplifier to get the IF amplifier, and then coming to the next part, this is the second mixer, active filter, and then meter. So this is the high frequency wave analyzer. And then after the high frequency wave analyzer, the next instrument is harmonic distortions. So this is not the distortion, this is the distortion, I'm sorry, this is the distortions. There are three types of harmonic distortion circuits. The first one is tunable selective circuits, and then heterodyne type, and then distortion measuring component. For the tunable selective circuit, we can see here in figure 3.6. We have the input, so the signal that we want to analyze the harmonic distortion coming to the input, and then going to the attenuator, and we have the local oscillator here to adjust the frequency of the signal. And then after, from the attenuator coming to the amplifier circuit, and then also tunable amplifier to amplify the signal, and then going to the VTVM. VTVM is vacuum tube voltmeter. So this is the vacuum tube voltmeter. Okay. And then the disadvantage of this tunable selective circuit is at a low frequency, the size of L and C is very large, because we use the attenuator, and also we use the amplifier circuit and tunable amplifier, so we need the size of LC. So in low frequency we need component L and C in very large, so it's like we need more space here. And then the second disadvantage of the tunable selective circuit is the harmonics of the signal frequency are very close to each other, so it's difficult to distinguish between them. And then the second option of the harmonic distortion is the heterodyne wave analyzer. We can see here, after the input coming to the attenuation, we have the balance mixer here, and then also we have a tunable oscillator to tune what frequency of interest. And then after we got the mixer, we get the IF frequency or another frequency coming to highly selective amplifier, and then coming to vacuum tube voltmeter. Okay, so because we use the tunable oscillator here in the heterodyne wave analyzer, we can tune the frequency in the local oscillator. So the frequency range of the heterodyne wave analyzer is more flexible than the tunable selective circuits. Okay, so that is the heterodyne wave analyzer. Yeah, then we also have the another heterodyne wave analyzer here. We have the if signal coming to the input attenuator, and then this is from the 0 to 80 megahertz coming to a tune amplifier, and then we have the local oscillator here and also first filter to fill, and then we got the signal in IF frequency around 30 megahertz, and also we can tune the local oscillator because we have the frequency range and frequency tuning here. After from the first filter, we going to the IF amplifier, second filter or second mixer, and then going to the active filter sections from 0 to 1500 megahertz, and then we can analyze the harmonic wave in the metal amplifier and detector here. Okay, So the frequency range of this instrument is around 10 kilohertz to 80 megahertz. And then the bandwidth of this active filter, uh, we can tune, we can select the 200 or 1000 or 3 kilohertz. Okay, so this is, and then after the heterodyne wave analyzer, we have the tune harmonic analyzer. We have the block diagram, we have the input here, and then we have the resonance circuit tuning to the frequency. So this is the resonance circuit, and then we can tune the L1, C1, and R1. So the frequency coming to the transformer here is suitable with our frequency of interest. And then we going after tune by the resonant, we going to the trafo and then going to amplifier, rectifier, and then we got the method here to analyze the harmonic. So the advantage of this instrument is for low frequency, we need a very large L1 and C1 here. And then the harmonics of the signal frequency are very close to the frequency. So the distinguish between the signal frequency and the harmonic is very difficult. So this is the tune circuit harmonic analyzer. The disadvantage of this tune circuit harmonic analyzer is similar with the tunable selective circuit. So the heterodyne wave analyzer is better than two kind of the harmonic analyzer. Okay, I think this is all of my presentation today. Thank you very much and good afternoon.